Alright, today we're going to be talking about magnets. Now, we're starting off with section 19-1, which is about magnets and magnetic fields. Some of this should be very familiar to you from previous science classes. Some of it might be a little bit new. Now, some things we know about magnets. There are two ends on a magnet called poles. And there is a north pole and south pole, and it might help if I spelled correctly, on every magnet. So most of the time they are marked N or S. Sometimes though they just have a dot. Just kind of depends on what kind of magnet you're looking at. Now, one thing about magnets is if you were to take a magnet and break it in half, like the one I just showed you, each piece would still have a north and south pole. And each time you break it, each piece still has a north and south pole, even down to the atomic level. Because it's the electrons moving in the atoms themselves that causes the magnetic fields. Now, we use magnets in a lot of different things. We use them in motors and loudspeakers, which we'll talk more about later. We'll talk probably more in chapter 20 than chapter 19. Recording data, VHS and cassette tapes, the black tape in those, that was magnetic tape that they used to record data. Credit cards, the black strip in your credit card is actually magnetic. A compass, like this one, is actually a magnet that's able to spin freely on a pivot. We use it in maglev trains. Maglev stands for magnetic levitation. And all kinds of other stuff, which some of it we'll talk about, but I think that's enough for now. Now, more about a compass. One thing about a compass is, yes, you have these kinds where you've got this pole right here. This is actually a magnet. The red end with the dot here, that's the north pole of the magnet, and it's able to spin freely on a little pivot. But you can also get the same effect just by taking a magnet and tying it to a bit of string. I don't know if y'all can see the fishing line I've got here, but if I were to just hold this and let it spin freely, eventually it'll stop moving and the north ends up pointing somewhere this direction, which is north for our room. Okay. That's why this one is pointing that direction, because north is in that general area. Now, some things that we know about magnets. Again, this should be old news to you. Like poles will repel one another, and unlike poles will attract. So, for instance, grab one of my magnets here. Okay, if I put two I've got kind of weak magnets here. There we go, that's better. So if I put two north poles together, you can see that they're repelling. But if I put a north and a south together, we can see that they attract. Now, it is possible to turn something that's not a magnet into one. So, for example, if I take a paperclip by itself is not a magnet. However, if I were to take the paperclip and rub it on a magnet, a permanent magnet, I can actually make this magnetic. And to prove it, you can tell because my compass is reacting to my paperclip. So you can actually turn something into a permanent magnet. Okay. Now, magnetic material can be classified as either hard or soft, depending on how well it retains its magnetism. Now, if something is easily magnetized, that's a soft magnetic material. But on the other hand, it's going to lose the magnetism very easily. So, for example, iron, or my paperclip, which is steel just now, that was a soft magnetic material. Now, if something is a hard magnetic material, it's very difficult to magnetize, but once it is, it stays that way. So something like cobalt would be a hard magnetic material. Now, a magnetic field is a region in which a magnetic force can be detected. So anytime you have a magnetic object, like whether it's an actual magnet or an electromagnet or something like that, if anything like this paperclip, there's a field around this where there isn't a magnetic force able to be detected. If I put it just kind of close, we can see that there's a force pulling the paperclip towards the magnet. Now, there is a magnetic field. It's not visible to our eyes, but there is one. Now, the direction a magnetic field points is the direction that the north pole of a compass will point at that location. So going back to here, got my magnet. Now, the north pole of my compass, it points away from my north pole, but towards the south pole of my magnet. Okay, so if you were to draw the magnetic field around a bar magnet, the field lines would move away from the north but towards the south, kind of like this. So the field lines, the magnetic field lines, go out of the North Pole and towards the South Pole, just like birds migrating in the winter, out of the north into the south. The other thing is that the strength of your field will be strongest when you're close to the poles. So let me show you a magnetic field. I'm going to take my magnet. Let me zoom out a bit. Okay, apparently it's not going to let me zoom out in this mode. Oh well. So if I take my magnet, I'm going to put a sheet of white paper on top, and I'm going to sprinkle some iron filings on top. You can see the shape of the magnetic field. You can see that they're kind of going like this, but at the poles they kind of stick straight out a little bit. And you can also see that I get more of it gathered at the poles. Let me try it again, but with a little bit less. Okay. Now, you probably can't tell, but some of the iron filings are actually sticking straight up rather than just laying flat on the paper. So not only do we have the magnetic field lines parallel to the paper, we also have them coming in and out of the paper, which is going to be important to remember here in a moment. Okay. Now, magnetic field lines, again, can be represented by using arrows. Just like what I did on this diagram, I used arrows to represent the direction of my magnetic fields. But as I showed you with the iron filings, you can also have magnetic fields going into or out of the page. Okay, so think of an arrow, but not just, drawing an arrow like I did on the previous slide, but an actual arrow that you might shoot from a bow. If you were to be looking at the head of the arrow, if I were to turn my arrow to where it was coming out of the page, you'd be looking at the pointed end of the arrow. And it might look like a dot, because you're looking at the pointed end of it. The dot represents out of that the field or current or whatever it is coming out of the page. Okay, so a dot means your magnetic field or current or force, depends on the situation, but it means that it's coming out of the page. If you're looking at this end, this is called the fletching, the feathers might make a pattern like an X. This means it's going into the page. So an X is into the page, a dot is out of the page. And again, you're going to be using that in this chapter quite a bit, so don't forget these symbols. Alright, so we know that the north pole of a magnet, of a compass, the north pole of a magnet, which is also a compass is a magnet, always points to geographic north. Okay, but here's the thing. We know that like poles repel, so if the north pole of this compass is pointing north, geographic north is actually magnetic south, because it's unlike poles that attract, and geographic south would be magnetic north. So let me prove it to you. North pole of a compass, north pole of a magnet, they're repelling. So my compass is actually pointing towards magnetic south. So this means that if you were to think of Earth as a magnet, we've got north and south pole, but the magnet of Earth's magnetic field is actually the other way around. So the magnetic field lines of Earth actually go like this. Okay. So let's look at this practice problem. Which compass needle is pointing in the direction for the magnetic field? If you'd like to try this problem for yourself, you can pause the video and answer it, and unpause when you're ready to check yourself. But the compass needle that's pointing in the correct direction is A. If B was correct, it'd be pointing to the right. Same with this one. C should be pointing that way. Alright, another practice problem. In order to protect other equipment, the body of a satellite must remain unmagnetized, even when the coils have been activated. So would it be better to make the satellite out of a hard or soft magnetic material? Again, if you'd like to debate this or talk amongst a friend, you can pause the video. But the answer is it's better to make it out of a hard magnetic material. The reason is because it's more difficult to magnetize. If at all possible, you don't want the satellite to become magnetized at all. If you made it out of soft magnetic material, it would happen too easily, and it would harm the equipment. So hard magnetic material is better because it's less likely to become magnetized. Alright, this is it for 19.1, and I will do a separate video for 19.2.